Conductor. A conductor with a length of 2a, and we show that down here. Here's the conductor. Carries an electric current I in the positive y direction. What is the direction of the magnetic field at point P? Determine the magnitude of the magnetic field at point P. Then if we place the proton at point P, which is moving at speed v in the positive x direction, what is the direction of the magnetic force on the proton? We now replace the conductor with a very long wire carrying the same current. What is the new magnitude of the magnetic field at point P? What is the direction of the magnetic field at point P? Use the right-hand grip rule. Grip the wire with your right hand, with your thumb pointing in the direction of the conventional current, and then wrap your 4 fingers around until they touch your palm, and that gives you the direction of the magnetic field. So at this point here, you'll find, hopefully, that it's into the page. Determine the magnitude of the magnetic field at point P. We're going to use the Biot-Savart law, and actually we did this in the presentation. However, a key difference is we have a finite wire. It's only going from negative A to A. It's not an infinite wire. And what else is different? We're going to do the algebra a little bit different. The algebra and trig will be a little bit different this time. So we know the direction of the field. Okay, it's into the page. Anywhere on the wire, you'll get that. You determine its magnitude by finding the absolute value of the cross product for dB, and then expressing it in terms of x, that's how far away you are, and this angle here, well, this angle here, theta. The contribution to the field by each line segment dy, here's our dy. You know what, I probably should start erasing already. Okay, so we have dy there. We'll add them all together, and the way we'll do it, we'll sweep out this entire length here, this length, by integrating from theta 1 to theta 2. Let's start evaluating Biot-Savart. We'll start with the cross product. The magnitude of the cross product is going to be the magnitude of each piece, which is dy and r hat. Well, the magnitude of dy is just dy. The magnitude of r hat, it's a unit vector, so that's 1. And then what do you want? You need the sine of the angle between them. So that's going to be phi, okay? We don't want to work with phi, we want to work with theta, so the sine of phi is equal to the cosine of this angle. So the sine of phi gets replaced by dy cosine theta. Okay, now let's keep going. Let's call this piece y, and this is x, okay? What is y equal to in terms of x? Well, tan theta, and again, here's the angle we're working with, is y over x, so y is equal to x tan theta. You now take the differential of y, see, because we need it up here, so that will be x is a constant now. That's the distance from the wire to P along the x-axis, so that comes out, and the differential of tan theta is secant squared theta d theta. So we replace the cross product with this expression. And that's different from what we did in the presentation, but of course it's equally valid. Now we'll work on the denominator here, the r squared. First we'll express r in terms of x and theta. Well, here's x, here's r, here's theta. So r cosine theta is x. Okay, now let's be careful here. R is going to change. R is a variable, right? Depending on where our ds is over here, r will change, but x will stay the same. So r is equal to x over cosine theta. Here's Biot-Savart. And then we put in everybody we found from the past couple slides, right? So hopefully you remember that. That's the I dy cross r. And the I, of course, comes out in front. It's a constant, as is mu 0 over 4 pi. And then here's r, and let's make sure we square it. It's now time to get rid of some of these trig things. So we have this from the previous slide. And what are we doing? We bring cosine squared theta up to the top. So we have cosine cubed theta, secant squared theta here. And we have the x squared. We pull that out front because, of course, that's a constant. And we divide out. And here is the magnitude of our dB. Mu 0 I over 4 pi x, cosine theta. d theta. To find the magnetic field at point P, we will integrate the dB we found on the previous slide from theta 1 to theta 2, and that will sweep out the entire length of the wire from negative A to A. First, we're going to express the limits of integration in terms of the given A and X. Why? You'll see on the next slide. It's kind of cool. So theta 1 is the sine inverse of A over R. And what is R equal to? That's the square root of A squared plus X squared. Theta 2 is going to be the sine inverse of A over square root of A squared plus X squared. So why was one negative A and one was A? Well, theta 1 goes to negative A, and theta 2 over here is attached to A. Okay, so the only difference between the two of these is the sign of your numerator. Here is the magnetic field, and see how we put the limits of integration in there? Okay, it looks a little messy, but a couple more lines down, you'll see how cute it becomes. And we're basically integrating cosine theta d theta. This is a constant, this comes out here. And then we get the integral of cosine theta d theta, of course, is sine theta. And we evaluate it at our two limits, which have the sine inverse function. Okay, so we expand it out like this. And now comes the cute part. What's the sign of the sine inverse? Well, it's just the argument here. Okay, so it'll be A over the square root of A squared plus X squared. Then the sine of the sine inverse of this will just give us negative A over the square root of A squared plus X squared. We have a minus here. Well, let me just erase here so we can see the minus clearly. This minus turns this minus into a plus. So we just have A over the square root of A squared plus X squared plus A over the square root of A squared plus X squared. That's this term here. Multiply people out, and this is our magnetic field. If a proton placed at point P moves at a speed v in a plus x direction, what is the direction of the magnetic force on the proton? So proton's up there at point P, moving in that direction. Use the right-hand rule. Align your four fingers in the direction of the charge's motion, and that's this guy right here, the arrow. Face your palm in the direction of the magnetic field, which is into the page. We found that out earlier. Your thumb should be pointing in the up direction to the top of the page. So this is the force on the proton moving to the right. If the length of the conductor is replaced with a very long wire carrying the same current, what is the new magnitude of the magnetic field at point P, where the distance there is x? The phrase very long wire enables us to treat the conductor as an infinite wire. The magnetic field due to an infinite current carrying wire is this, so we replace the r with x and we get this answer here. Another way of doing this is use the expression we just calculated for the wire of length 2a, this guy right here. If the wire is very long, that means that a is going to be much, much greater than x. Therefore, wherever we have a squared plus x squared, we'll go ahead and replace that with a squared. So here's our formula for the wire of length 2a. And what are we doing here? We're going to look at this guy right here, replace that with just the square root of a squared. Well, that of course is a. That cancels out this a up here. And we get the same answer, which is very nice. U0I over 2 pi x.